Welcome to the deep dive. It's late.
Yeah, really late.
Maybe you're driving home right now. Maybe you're just like staring at a terminal window that's been open way too long.
We've all been there.
Right. Just watching the cursor blink in the dark while some deployment runs. We know who you are. You're a software engineer, a systems architect, a builder. And I mean, if you are building anything right now, you are relentlessly bombarded with AI hype.
Oh, constantly. It's inescapable.
Every single day there is, a new model, a new framework, some new thought leader on Twitter promising that this specific piece of magic is going to solve all of your back-end latency and scaling problems.
Right, just the silver bullet.
Exactly. But tonight, we're turning the volume down on all that hype. We are cutting through the noise to solve a very real, very practical engineering dilemma.
And it's a big one.
It is. We're looking at notes from episode 74 of the LLM Mastery podcast. The session is titled, Why Fine-Tune When Prompting Isn't Enough. And our mission for this deep dive is extremely specific.
Extremely.
We want to find that exact line in the sand, that architectural threshold where prompting officially fails, and fine-tuning transitions from being like a shiny resume buzzword to the absolutely necessary logical next step in your engineering stack.
Because it is arguably the most critical architectural decision teams are facing right now. I mean, in a landscape characterized by severe tool fatigue, understanding precisely when to pull the fine-tuning trigger dictates everything.
It's everything.
It dictates your infrastructure costs, your latency overhead, and ultimately, your team's sanity. You don't want to bring a sledgehammer to crack a nut, but you also cannot afford to bring a butter knife to a demolition job.
Yeah, that's a great way to put it.
We need to map out the mechanical and economic realities of making that exact call.
Okay, let's unpack this, because before we jump into altering model weights and all the heavy lifting, the source material draws a really hard line on what we should be doing first.
Right, the baseline.
Exactly. There's this don't fine-tune yet rule. The notes insist that prompting is not just, typing a zero-shot question into a text box. It's an entire engineering spectrum.
The progression.
Yeah. You start zero-shot. If that fails, you build a many-shot prompt, right?
Huh.
With specific input and output examples.
Give it some guardrails.
Right. And if that's still failing, you move to RAG retrieval augmented generation, where you fetch proprietary data from a vector database and inject it into the prompt context at runtime. And the source is adamant that engineers need to completely exhaust this spectrum before even considering fine-tuning.
Because the baseline assumption for any modern architectural design should be that the base model is actually capable, provided it has the necessary context.
Okay, right.
But think about the mechanics of what happens during that prompting spectrum. Zero-shot, many-shot, they're all mechanisms for leveraging the model's temporary memory, its context window.
Suckerpad. Exactly. RAG is incredibly powerful because it grounds the generation in your up-to-date facts without needing to touch the model's underlying neural network. You are basically giving the model an open book test.
I love that analogy.
Right, allowing it to read the reference material right there in the exam room, rather than forcing it to permanently memorize a textbook that's just going to be outdated by next Tuesday anyway.
Yeah, I look at this through the lens of traditional software development, like jumping straight to fine-tuning because your zero-shot prompt hallucinated once.
It's madness.
It is. It's like deciding to rewrite an entire open-source library from scratch just because your very first API call returned a 400 error.
Yeah.
That's a massive overkill.
Yeah.
But looking at the industry right now, I have to ask, are development teams just getting, fundamentally lazy with their prompting structures, or is fine-tuning just the shiny new toy developers desperately want to play with?
I mean, there is absolutely a shiny object syndrome at play here. Engineers are builders.
We like to build. We do. Setting up a gradient descent pipeline feels like real engineering, whereas prompting can sometimes feel like trying to negotiate with a stubborn black box.
Like whispering to a ghost.
Exactly. But your analogy of the API call versus rewriting the library hits the core issue, and that's technical debt.
Huge debt.
When you write a complex prompt or build a sophisticated RA pipeline, you are dealing with stateless interactions. The model itself remains an external managed service. But the very millisecond you decide to fine-tune,
You cross the Rubicon.
you cross a massive threshold. You are creating a net new stateful asset.
Yeah.
You now own the hosting, the version control, the continuous evaluation, the security patching,
You own all of it.
all of it. You are taking on a mountain of technical debt, so you have to mathematically and architecturally prove that the debt is necessary.
Okay, so where is that wall? Like if RAG is the absolute ceiling for stateless interactions, when does that API call definitively break down? The source outlines the transition into specific scenarios where fine-tuning isn't just an option, it's the definitive engineering solution. They break this down into 4 pillars.
The 4 pillars, yeah.
Yeah, and if your use case falls into these buckets, you stop prompting and you start tuning. Those pillars are specialized domain knowledge, consistent output formatting, behavioral reliability, and cost-efficient, high-volume inference.
Those pillars form a really rigorous framework for evaluation. Let's look at the first, specialized domain knowledge. This isn't just about knowing a few specific facts.
Right, it's deeper than that.
Way deeper. It's about the fundamental vocabulary and structure of the data. A generalist model has a broad, latent space. But if you ask it to parse incredibly niche medical diagnostics or highly specific, archaic legal contracts, it struggles.
Because it's never seen them.
Right, it lacks the internal representation of that domain entirely.
So to put that in software terms, could we compare that to trying to prompt a standard model to understand a massive, undocumented 30-year-old COBOL code base, or maybe some highly proprietary internal API schema?
That is the perfect scenario. If you
Yeah.
try to use RAG for a massively complex, intermingled proprietary code base, you'll just end up stuffing thousands of tokens of context into every single prompt.
Just to explain what things mean.
Yeah, exactly. Just to explain the basic syntax and dependencies before you can even ask your actual question. You hit the context window limits instantly.
And it gets lost.
Yeah, the model suffers from the needle in a haystack problem, or it forgets instructions right in the middle of a massive prompt. Fine-tuning solves this mechanically.
How so?
By running your proprietary data through a training run, you permanently alter the neural pathways. You teach the model the language intrinsically, so you don't have to explain the rules of the road on every single request.
Okay, that makes sense. And I guess that leads directly into the behavioral reliability pillar. Because when you are dealing with edge cases in production, a prompt is really just a suggestion,
It's a
right?
follow-up request, yeah.
Right. I can tell a model, never guess if you don't know the answer, but in a live environment with thousands of unpredictable user inputs, it's eventually going to hallucinate.
Because prompting only acts as a temporary filter over the model's foundational training.
Oh, interesting.
Yeah, most commercial-based models are heavily optimized through reinforcement learning from human feedback, RLHF.
Right, to be helpful.
Exactly. They're trained to be excessively helpful and conversational. They inherently want to give you an answer. When you put a behavioral constraint in a system prompt, you are actively fighting against millions of hours of underlying training.
Wow.
But by fine-tuning for behavioral reliability, you use gradient descent to permanently shift the probability distribution. You physically rewire the model so its natural instinctive state aligns with your safety boundaries.
So it's not a rule anymore.
Right. It's the difference between telling an employee to follow a new rule for the day versus hiring someone who just fundamentally operates that way.
Okay, I follow the logic on domain knowledge and behavior, totally. But I really want to push back on pillar number 2.
Okay, let's hear it.
Consistent output formatting. We see this argument all the time, but I mean, can't developers just write a brutally strict system prompt demanding JSON output?
People try.
We do this constantly. You write, return only valid JSON. Do not include Markdown. Do not say, here is your JSON. Why take on the massive compute costs and technical debt of fine-tuning just to get your brackets and commas right?
What's fascinating here is that on the surface, it seems totally trivial.
Oh?
But mechanically, it comes down to a concept called attention dilution.
Attention dilution. Okay.
When you use a massive system prompt to demand strict JSON, you are forcing the model's attention heads to spend a significant portion of their computational power suppressing that conversational RLHF training we just talked about.
Oh, so it's working hard just to stay quiet.
Exactly. The model has to actively restrain itself from saying, certainly, here is the JSON you requested. It works most of the time in testing.
Sure, on your local machine.
Right. But at scale, say, over hundreds of thousands of asynchronous API calls, the probability of failure approaches certainty. It will eventually drop a trailing comma or wrap the response in a markdown block, and your downstream parsing pipeline will completely shatter.
And there is nothing quite like a production pipeline crashing at 2 a.m. on a Saturday because an LLM decided to be polite and add "have a great day" to the end of a Boolean payload.
Which is an absolute nightmare. Fine-tuning fundamentally removes that conversational urge for that specific task.
It kills the chatbot vibe.
Exactly. You aren't allocating precious attention mechanics to suppressing behavior anymore. You are changing the internal weights. so that the model's only concept of reality is outputting raw, unadorned JSON.
Wow.
It shifts the formatting from being a temporary forced rule to being the underlying nature of that model. It ceases to be a chatbot and becomes a dedicated, ultra-reliable data transformation function.
That makes the mechanics so clear. And that functional reliability leads us straight to the performance and architectural payoff, because the source notes drop a metric here that completely reframes model selection.
It really is.
Here's where it gets really interesting. It's a classic David versus Goliath scenario. The notes state that a fine-tuned small model, specifically something in the 7 to 8 billion parameter range, can match and frequently destroy a prompted large model that sits at 400 billion parameters or more.
Assuming the task is narrowly defined.
Assuming the task is narrowly defined, yes.
It forces us to abandon this assumption that parameter count is the only viable proxy for intelligence or capability. A 400 billion parameter model is a marvel.
It's massive.
It has read a massive chunk of human history. It can translate obscure dialects, write complex Python scripts, and explain the intricacies of astrophysics.
Right.
But if your application's only job is to parse unstructured user logs and extract email addresses, 392 billion of those parameters are dead weight.
They're just sitting there.
Just sitting in VRAM, burning electricity, and adding massive inference overhead to your API calls.
For the system architects listening, think about it like this. Relying on a massive 400 billion parameter generalist model to execute a specific background task is the exact equivalent of deploying a massive, painfully slow, monolithic application where all the code for every conceivable feature is tangled together.
Yeah, giant monolith, yeah.
But taking a 7 or 8 billion parameter model and fine-tuning it, that is building a hyper-optimized, lightning-fast microservice.
Perfectly said.
It doesn't know anything about astrophysics, and it doesn't care. It just takes your unstructured log data and fires back perfectly formatted JSON in milliseconds. It is literally the microservice architecture applied to generative AI.
And taking that microservice analogy a step further, look at the physical deployment advantages.
Yeah.
A 400 billion parameter Goliath requires a massive, highly expensive cluster of top-tier GPUs.
We're talking big money.
We're talking tens of thousands of dollars a month just to load the model weights into memory, let alone actually run inference.
Yeah.
But a 7 billion parameter model can run on drastically cheaper, readily available hardware. It can run on a single commodity GPU. In many cases, it can run locally on edge devices.
Which changes everything.
It does. You drastically reduce your time to first token. You eliminate network latency if you host it close to your application. The efficiency gains across the entire compute stack are just staggering.
Okay, so the microservice wins on speed, latency, and reliability. But, I mean, as anyone who has ever built software knows, eventually you have to justify this to the finance team.
No, always.
We have to map out the economic calculus and, more importantly, the long-term reality of maintenance that the source material heavily emphasizes.
The economic case is actually the easiest part to calculate, provided you have good telemetry. It comes down to inference cost savings.
Walk me through that.
When you fine-tune, your prompts becomes significantly shorter because you no longer need to stuff the context window with many-shot examples or massive RGI payloads.
Oh, right. Fewer tokens.
Exactly. Fewer input tokens mean cheaper calls. Furthermore, you are running inference on a 7 billion parameter model instead of paying the premium API rate for a 400 billion parameter giant. Your cost per API call just plummets.
That makes sense.
You take that savings per call, multiply it by your expected daily volume, and map that against the upfront engineering and compute costs of the training run.
Yeah.
If those inference savings cover the fine-tuning costs within a single quarter, the business case writes itself. You pull the trigger.
That covers the fourth pillar perfectly. Cost-efficient, high-volume inference. But the source is brutally clear that the initial training run is not the finish line.
Not even close.
You don't just fine-tune a model and go to the beach. They emphasize that fine-tuning is an ongoing maintenance commitment. We have to deal with base model updates, evaluation infrastructure, and specifically something called data drift. Coming from traditional database management, data drift sounds like schema migration issues or data rot. Is data drift basically what happens when your fine-tuned model's static, locked-in weights inevitably collide with a rapidly changing real-world environment?
If we connect this to the bigger picture, you're hitting on the core issue of stateful ML assets. Data drift is the reality that the live data flowing into your application changes, while your model's weights remain frozen in time from the day you trained it.
So it gets stale.
Exactly.
Mm.
Suppose you fine-tune a model to route customer support tickets based on your product catalog. It achieves, say, 99% accuracy.
Sounds great.
6 months later, your company acquires a competitor, launches a dozen new products, and completely restructures its pricing tiers.
Ah.
The live data hitting your API has drifted entirely away from the distribution the model was tuned on. Because the model is so highly specialized, it will start making confident, high-speed errors, routing tickets into oblivion because its intrinsic knowledge is now obsolete.
It's a living piece of software that can decay, which means fine-tuning isn't a deploy and forget situation. You are essentially trading unpredictable prompt engineering headaches for traditional CI/CD and data pipeline maintenance.
And that is a trade-off professional engineering teams should gladly make because it replaces unpredictable third-party API changes with manageable, systematic internal processes.
Right, it's under your control.
But you have to build the infrastructure. You cannot just deploy a fine-tuned model. You must continuously run automated tests against it, using golden data sets to monitor its accuracy over time.
That sounds like a lot of work.
It is. Furthermore, the open source community moves fast. When a dramatically better foundational 8 billion parameter model drops, one with a vastly superior base architecture, you need the automated data pipelines already in place to rapidly rerun your fine-tuning process on that new base model.
Got it.
It requires a dedicated MLOps pipeline, treating model weights with the exact same rigorous testing and deployment standards as compiled code.
So what does this all mean? The journey here is incredibly revealing. We started out trying to find the exact threshold where we abandon prompting and embrace fine-tuning.
Right.
The baseline is doing the hard work up front, exhausting the zero-shot to many-shot spectrum and building robust R-grade architectures to keep interactions stateless and cheap.
Absolutely.
But when you hit the wall, when your generalist model fails at deeply specialized domain knowledge, when your downstream pipelines shatter because of formatting hallucinations, when you need intrinsic behavioral reliability, and when your volume makes massive prompt tokens economically ruinous.
That's the moment.
That is the threshold. That is when you shrink the 400 billion parameter monolith down into a hyper-optimized 7 billion parameter microservice. You take on the technical debt, the CI/CD pipelines, and the MLOps overhead because the architectural and economic payoffs demand it.
It represents a complete maturation in how we architect intelligent systems. We are moving away from treating AI as this magical black box and starting to treat it as a configurable component in a broader engineering stack.
A real engineering tool.
Exactly. And the notes indicate the LLM Mastery podcast takes us even further in their next segment. They dive into the physical methods of fine-tuning, starting with the most resource-intensive approach, full fine-tuning, where you unfreeze and update every single parameter in the neural network before exploring more efficient methods like LoRa.
Oh, that is going to require a deep dive into GPU memory constraints and gradient updates.
It gets technical fast.
It really does. But for tonight, as you close your IDE or as you finally pull into your driveway, I want to leave you with a thought to mull over.
Okay.
We have been culturally conditioned to picture the endgame of artificial intelligence as a single, massive, omnipotent 100 trillion parameter brain sitting in a centralized server farm somewhere, trying to be everything to everyone.
The giant brain in the sky.
Right. But if a tiny, highly optimized 7 billion parameter model can be trained to completely outsmart a 400 billion parameter giant on a specialized task, it begs the question, is the true future of software architecture really going to rely on that single, massive, generalist brain? Or is the future actually just the thousands and thousands of highly specialized, perfectly fine-tuned micromodels, all quietly passing JSON payloads back and forth, running the world together in the background?
That's a profound way to look at it.
Keep building, and we'll see you on the next deep dive.